So here are a few problems from the unit on fluids, and I'm going to start with this one here, the mercury. Mercury is commonly supplied in flasks containing 34.5 kilograms, about 76 pounds. What is the volume in liters of this much mercury? So just use the density equation, and first I have to convert the kilograms to grams, and that is because the density by which it is divided, the 13.6, if I'm ever able to actually plug that in. So density for materials is usually given in grams per cubic centimeter, so convert to grams, so the grams divide out, and what remains is cubic centimeters, 2,540 cubic centimeters. And then to get it over to liters, there is 1,000 cubic centimeters in 1 liter. Cubic centimeter is also the same thing as milliliters, so 2.54 liters. Picture a soda bottle that is filled with mercury. Well, don't put mercury in it, it's poisonous, but just picture it, and that soda bottle full of mercury is a whopping 76 pounds. Mercury has a density that's even larger than lead. All right, I'm going to take a short break before I go to the next problem. All right, so here, what force must be exerted? What force must be exerted on the pedal cylinder of a hydraulic lift to support the weight of a 2,000 kilogram car, a large car, resting on the wheel cylinder? The pedal cylinder has a 2 centimeter diameter and the wheel has a 24 centimeter diameter. And so using Pascal's principle right here, which is that the pressure equals the same everywhere inside the fluid. So force divided by area. The area, it's a cylinder, so it's a cross section is a circle, so it's pi r squared. Notice that the pi actually divides out, and it's obviously just the ratio of the radii squared. So 24 divided by 2, which is 12, squared it, 144. Divide 144 into 2,000. So like this. And that would be the mass of the that would be exerted, but you cannot exert a mass, so you have to say, well, how much force in newtons. So that means that the mass of the car has to be multiplied by the gravity, so times 9.80. That gives us the weight of the car close to 20,000 newtons, but as far as the input force is concerned, much less, the factor 144, and that is the rounded 136 newtons. So to lift a car 2,000 kilograms, which is about 4,500 pounds, all you need is 136 newtons, which is in the neighborhood of 30 pounds. That's really all you need with this hydraulic pump. I found, let's see, this little video here where this guy, for some reason, wants to build a, let's see if we can see the title here, wants to build a 4-post lift in his garage. I'm going to turn this one off, and here he goes. And there we go. And yeah, pumping the fluids through the hydraulic system, he's then able to lift his car with relatively little force. Of course, he has to pump and pump and pump. Okay, this one here, I wish they would have done a little bit slower so we can actually see that. Okay, anyway, there he is. All right, give myself a break before I do the next problem. So this one here, bird bones and so on. And bird bones have air pockets in them to reduce their weight. This also gives them an average density significantly less than that of the bones of other animals. Suppose an ornithologist weighs a bird bone in air and in water and finds its mass 45.0 grams which is ounce and a half, and its apparent mass when submerged is 3.6 grams. The bone is watertight. What mass of water is displaced? What's the volume of the bone? What is its average density? In my physics lab, I have this particular experiment in order to determine what is called the immersed mass or effective mass, and I think it's called the apparent mass here, which is on the left. So for the apparent mass, I'm sorry, it's the effective mass, it's on the right. So for the effective mass, you put it on a scale and then immerse it in water and determine then how much it weighs how much less due to the buoyant force, and that gives you that effective or apparent mass. And the formula for that is this one down here. Mass, the original mass that you just put the bone on the scale of 46 grams, you divide by the difference between the two. So 46, what was it again? 46 minus 4.6 or something? 45 minus 3.6. And that gives you then the density respectively first, because you divide grams by grams, you actually get specific gravity, which has no units, as I say right here. And then you convert it to density in grams per cubic centimeter simply by multiplying with the density of water, which is 1.00 grams per cubic centimeter. So doing that, let's see. Where's my calculator? Where's my calculator? There's my calculator. All right. And so doing that would be then, what was it again, 45.0 divide by 45.0, as I just showed you that equation there, minus 3.6, parentheses, enter, and that is the rounded 1.09 grams per cubic centimeter. And because it's a little bit more dense than water, that's why it's able to sink in the water, and you have it immersed in there and well determine the effective mass. In this case here, the way with my formula, I didn't need the other two equations, but yeah, in order to determine here, this is actually, here it is, mass, displaced mass, right, and 41.4 grams, and as the mass displayed of the water is being displaced, which then is the same number for the volume of water, and therefore also the volume of the bone, because for the 41.4 cubic centimeters, since it's a volume, because again the density of water is exactly 1.00, and then you come up with this number here as well. The bird doesn't swim in water, so it would actually, the bone actually would sink in water, but the bird of course flies in air, and still of course it needs lift from the wings, but at least that makes the bone less heavy, and therefore it's just easier for the bird to fly. Alright, took a little break to go to the next problem. So here's a number of videos. By the way, this is a different kind of video here, the hydraulic lift table, some mercury, and so on. Here's the pumping blood, and then there's a video here on sailboats. So let's see, the one that I wanted to do is, or the third one, blood is pumped. So blood is pumped from the heart at a rate of 5 liters per minute into the aorta. 5 liters, that's a gallon and a half every minute is what our heart is doing. The aorta has a radius of 1.0 centimeters. Determine the speed of blood through the aorta, and here would be the flow rate formula. The flow rate given in volume, cubic centimeters, times, divided by the amount of time, so cubic centimeters divided by seconds, and that's what's given here. The 5.0 liters, or 5,000 cubic centimeters, divide by 60 seconds, it's 1 minute, and that then divide that by the cross-sectional area, and that gives you the speed of the blood in this case. And again, I have to find my calculator. There we go. I'm going to find my calculator here on my screen. So it's the 5,000 divided by 60 divided by pi divided by the radius squared, but of course 1.0 squared is still 1, and I come up with the same number here, 2 sig fig apparently, yeah, 1.0, 5.0, exactly 1 minute, 27 centimeters per second, which means the blood flows at a speed about 1 foot per second. So going from the heart to the feet, it only takes about 5 seconds to get there. All right, again, a little break. All right, let's see, force on a sail. That's the last problem that I want to do. And the problem says this: calculate the approximate force on a square meter of sail, given the horizontal velocity is 6 meters per second parallel to its front surface and 3.5 meters per second along its back surface. Take the density of air to be 1.29 kilograms per cubic meter. Notice this is in kilograms per cubic meter. Kilograms per cubic meter, which is, if you put it in grams per cubic centimeter, is only 0.00129, so much smaller than other materials, because air has much smaller density. Calculation based on Bernoulli's principle is approximate to the effects of turbulence. Discuss whether this force is great enough to be effective for propelling a sailboat. So here it is, here's the algebra. Bernoulli's law, pressure plus the 1/2 density velocity squared. Looks like kinetic energy, and actually, yes, it is related to that. The one part that's missing here would be the potential energy, which then is density times gravity times height, because it's virtually the same height here between the one part of the sail and the other one. And so rearranging terms here respectively using force equals pressure times area, pressure equals force divided by area, and then subtracting this one here, we come up with this expression, and then when we plug in numbers, just like it shows there, so the 0.5 in the front here times the density, and then times square the velocity here minus the other velocity here, and that squared, both of them squared independently, and then times, it says per square meter, so just a times 0.10 here squared, still 1, enter. And so that's the pressure differential. I'm sorry, so to say the pressure differential be between one surface and the other one, and because it's already multiplied by the area, it's the force that is exerted, 15.3 newtons, which is in the neighborhood of 3.5 pounds. And as they say here, this force seems to be small, but sails are large, so you could actually get enough force that is applying for a larger sailboat. And I confirmed this number. Keep in mind, I just said a moment ago when I converted 3.5 pounds per square meter. So I found this website here, calculating sheet loads, and this is about sailboats. And here at moderate speeds, 10 miles per hour wind speed, the pressure would rise to 0.256 pounds per square foot. A square meter is approximately 11 square feet, so when I multiply this here by 11, I come up with like 2.8 pounds per square meter. And I mentioned a moment ago that this one here, what I just calculated, was 3.5 pounds per square meter, so basically the same thing. And then of course it says, well, hey, a mainsail might be as big as 500 square feet, so you would have to multiply it with another factor of 50, and you probably get enough force there. All right, that was the last problem I wanted to do for this one here.